Hey, hello there, guys. We're going to go over Activity 232 here, Tensile Testing Simulation. And I'm going to help you get started with a little bit of this part. In this, they want us to start off, and it says procedure. You will use a tensile test simulator to observe how the test is performed and how the force displacement graph is created during the test. You will perform calculations using the graph to better understand the graph and important data. So here it says go to the virtual tensometer. Click enter to begin the simulation, and I'm going to demonstrate that for you. Choose want to try, alright. Then you're going to go to the image of the virtual tensometer. You're going to place one of these materials in here. It's going to do the test for you. You got these ones to choose from. Right now I'm telling you, do not do cast iron. Do not do cast iron. Alright, so then we need to go to that test. We're through all that. Now I will tell you that when I first tried clicking on this right here, it wanted to pull me up in Google Docs. And for whatever reason, when you click on it in Google Docs, it gives me this image right here. So if you're getting this as well, just simply copy this and go into Internet Explorer and it's going to work for you. So, right here, I'm going to grab a hold of the copper. Notice it says right here, you have selected copper. And it does a test for us. Alright, it's pulling on it, it's starting to neck, and then it breaks. Here's that failure point. And what we've got now then is a stress and strain graph for this information. What you guys are going to need to do is capture an image of this. I always use my snipping tool. Now I've got that ready. I'm going to go back in here. So now we're ready to start answering these questions. It says the greatest stress that a material is able of withstanding without deviation from the straight line proportionality between the stress and strain. That's the proportional limit stress. If the force applied to a material is released, the material will return to its original size and shape. So it says insert test graph here. So I've already done that. Now I've got my graph there. Alright. They're giving us the equation for the proportional limit of stress. And that's the force over the area. Well, what I'm going to do here then, the force then is the load. Well, how much is being applied? This is in kilonewtons, so I'm going to guesstimate this to be about 31,000. Alright, you could say 30,000, 31,000 kilonewtons. Alright, so I'm just going to go ahead and say 30,000 newtons. Alright, not 31,000 kilonewtons, but 31,000 newtons. So I've converted it here from kilonewtons to newtons. And I'm going to divide that by the area. Well, what's my area right here? Well, my area appears to be 1. And, you know, there's 2, so here's 1. Now, it's not 1. I was about ready to make the same mistake that a lot of students. This is in millimeters. So I've got to give this area, alright, I've got to give my area, let's backtrack here, up in the assignment. I didn't go far enough, went to the wrong spot here, in the assignment. Alright, the original diameter of the specimen is 5 millimeters or 0.2 inches, and the original length is 75 millimeters or 2.95 inches. This is important, alright? So, to find the area is equal to, for lack of better terms, I'm going to say pi r squared. So what I've done here is area is pi r squared because it's a cylinder here. There's pi. There's the radius. I changed 5 millimeters into meters, so that gave me 0.005 squared, and you get an answer of 0.0000785 meters squared. So that's going to be what I use for my area every single time, because this says every specimen is that way. So I'm going to use that number every time for my area of my specimen. So I'm going to go back here and change that. and it's 0.1234785. And now we can find out what is the stress that's been put on this. And we get an answer then that is equal to 382,161. Shoot, 5, not a 1. 5,605. All right, and that would be newtons per meter squared. All right, because my top was in newtons and this was in meters squared. So hopefully that helped you a little bit with that one. Yield stress point. So they want me to put this in here again. That yield stress point, all right, the point at which sudden elongation takes place while the load on the sample remains the same or actually drops. If the force applied to the material is released, the material will not return to its original shape. So right here is that yield point. All right, right here's that yield point. So we got a little practice with the equation. They want us again find the stress, all right, at the yield point. Well, what you're going to find out is it's not going to really be much different here, because again, our force is still here. All right, make sure I'm reading this right. The point at which the sudden elongation takes place, yes. All right. If the force applied to the material is released, the material will not return to its original shape. So it's going to be a little bit higher, because back here, all right, I was right when I said it's about the same. Right here we said 30,000. Once we go past that load of 30,000, so I'm just going to go ahead and say 31,000 for lack of better understanding, because we got to go past that point of proportional, past the proportional limit stress, and then I'm still going to use that same area. And it gives me just a slightly different answer. 3949044, and I'm going to go ahead and round it up to 6 newtons per meter squared. There we go. So now it's all in the same spot. Well, yeah, I'm not going to go through the rest of the assignment. That's up for you guys to do. But I've given you a pretty good idea of how to get started. I'll catch you guys on the flip side.